Quantum statistics. In quantum statistics, first is microstate and macrostate. In statistical mechanics, a microstate is a specific microscopic configuration of a thermodynamic system that the system may occupy with a certain probability in the course of its thermal fluctuations, while macrostate of a system refers to its macroscopic properties such as temperature, pressure, volume, and density. Statistical mechanics define macrostate as a particular set of values of energy, the number of particles, and the volume of an isolated thermodynamic system is said to specify a particular macrostate of it. A macrostate is characterized by a probability distribution of possible states across a certain statistical ensemble of all microstates. Thermodynamic probability. The number of processes by which the state of a physical system can be realized. That is, in thermodynamics, a system is characterized by specific values of density, pressure, temperature, and other measurable quantities. The thermodynamic probability is equal to the number of microstates which realize a given macrostate, from which it follows that the thermodynamic probability is connected with one of the basic macroscopic characteristics of the system, that is the entropy S, by the Boltzmann relation, that is S equal to K ln W, where K is the Boltzmann constant. The thermodynamic probability is not a probability in a mathematical sense. It is used in statistical physics to determine the properties of systems which are in thermodynamic equilibrium. Bose Einstein statistics. Bose Einstein statistics refers to a set of particles having quantum mechanical behavior. They do not obey Pauli's exclusion principle. In Bose Einstein distribution law, Bose Einstein system is composed of n independent and indistinguishable particles. Consider n indistinguishable particles that constitute the system. Let there be n1 particles in energy state E1, n2 particles in energy state E2, etc., ni particles in energy state Ei. If the degeneracy of the ith level is Gi, the total number of distributions, that is eigenstates for ni particles, is equal to the number of ways in which these ni particles can be distributed among the Gi states. In Bose-Einstein system, there is no restriction on the occupancy of each energy state. That is, in bosons, the occupancy can vary from 0 to infinity. That is, they do not obey Pauli's exclusion principle. The number of ways of obtaining such a distribution is given by the equation W is equal to ni plus gi minus 1 factorial divided by ni factorial into gi minus 1 factorial. The total number of particles are divided into groups of Ni and the particles are indistinguishable. There is only one way in which this subdivision can be made. Hence, the total number of ways of distributing n particles is given by the equation W is equal to product of I is equal to 1 n. Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. However, this distribution is subject to the conditions sigma Ni equal to n, that is a constant. Sigma I Ni here equal to E, a constant. Taking logarithm of equation 2, we get ln W is equal to sigma I ln Ni plus Gi minus 1 factorial minus ln Ni factorial minus ln Gi minus 1 factorial. By using the condition of maximum probability of this system and making use of Stirling's approximation and recognizing that Ni's and Gi's are large numbers, so that Ni plus Gi minus 1 and Gi minus 1 can be taken as equal to Ni plus Gi and Gi respectively. That is, we can omit 1. Then the equation becomes as ln W is equal to sigma I Ni plus Gi ln Ni plus Gi minus Ni ln Ni minus Gi ln Gi. That is given equation number 5. Using Lagrange's method of undetermined multipliers, by using equation 5, we get dou ln W by dou Ni star plus alpha minus beta Ei, that is equal to 0. From equation 5, dou ln W by dou Ni star is equal to ln Ni star plus Gi by Ni star. We can write the above equation as Ni star plus Gi by Ni star is equal to e raised to minus alpha plus beta Ei. That is, Gi by Ni star is equal to e raised to minus alpha plus beta Ei minus 1. Therefore, Ni star is equal to Gi by e raised to minus alpha plus beta Ei minus 1. That is given equation number 6. Equation 6 is the mathematical representation of the Bose Einstein distribution law or Bose Einstein statistics for most probable distribution of bosons among energy levels. It leads to the derivation of Planck's law for distribution of energy of black body radiations. This is one of the important applications of Bose Einstein distribution law. The most probable distribution can be written as Ni equal to Gi by e raised to minus alpha minus beta epsilon I minus 1. That is given equation number 1. Equation number 1 is Bose Einstein distribution. It gives the population of an energy level that has energy epsilon I and degeneracy Gi. The constants alpha and beta are determined from the constraints on the total number of particles and the total energy. Beta can, as usual, be related to thermodynamic temperature, so that Bose Einstein distribution takes the form Ni equal to Gi by B e raised to epsilon I by kT minus 1. This is the Bose Einstein distribution for a collection of indistinguishable bosons. Next is Bose Einstein systems, that is symmetrical eigenfunctions. It is a system of identical and indistinguishable particles. The wave function is symmetrical and the state of the system is determined if the number of particles in a given quantum state is known. There is no restriction on the occupancy of the particle in a given quantum state. Photons, alpha particles, neutron, and all atoms and molecules composed of even number of elementary particles like C12, N14, O16, etc. fall in this category. The spin of the nucleus is either 0 or an integral number. Such particles are called bosons. Next is Fermi-Dirac statistics. That is identical particles with the spin half that cannot be distinguished are Fermi particles or fermions. They obey Pauli's exclusion principle. Fermi-Dirac systems, that is anti-symmetric eigenfunctions. It is a system of identical and indistinguishable particles that satisfy Pauli's exclusion principle, which postulates that there is never more than one particle in a given quantum state. Fermi-Dirac system is formed by all elementary particles, namely electrons, protons, neutrons, positrons, antiprotons, neutrinos, etc., and by all atoms and molecules composed of odd number of elementary particles. These particles have a spin half or an odd integral multiple of half. Such particles are called fermions. Fermi-Dirac distribution. The Fermi-Dirac systems are composed of n identical and indistinguishable particles. The distribution of such particles in various quantum states is given by Pauli's exclusion principle. The total number of particles and the total energy of the system are constant. Let us consider the distribution of Ni particles among Gi energy levels of energy Ei. In this case, Gi is very much larger than Ni, such that maximum one particle can occupy a energy level. That is, the occupancy of an energy level is either 1 or 0. The number of ways of obtaining such a distribution is given by W is equal to Gi factorial divided by Na factorial into Gi minus Na factorial. The total number of waves for the whole system consisting of n particles would be W is equal to product of I equal to 1 n gi factorial divided by ni factorial into gi minus ni factorial. That is equation number 1. Taking logarithm, ln w is equal to sigma I ln gi factorial minus ln ni factorial minus ln gi minus ni factorial. Using Stirling's approximation, ln w becomes ln w is equal to sigma I ni minus gi ln gi minus ni minus ni ln ni plus gi ln gi, and dou ln w by dou ni star is equal to minus ln ni star plus ln gi minus ni star. That is equal to minus ln ni star divided by gi minus ni star. Upon using the condition sigma ni equal to n and sigma I ni equal to e and the Lagrange's method of undetermined multipliers, that is minus ln ni star by gi minus ni star plus alpha plus beta I equal to 0. ln gi minus ni star divided by ni star is equal to minus alpha plus beta ei. gi minus ni star by ni star is equal to e raised to minus alpha plus beta ei. gi by ni star is equal to e raised to minus alpha plus beta ei plus 1. ni star is equal to gi by e raised to minus alpha plus beta ei plus 1. That is equation number 2. Equation 2 is the mathematical representation of Fermi-Dirac distribution law for fermions. It is also known as Fermi-Dirac statistics. It is applied to study thermionic emission, electron gas in metals, semiconductors, etc. Fermi-Dirac distribution function. In a solid crystal, the free electrons possess different energies. According to quantum theory, at absolute zero temperature, the free electrons occupy different energy levels continuously without any vacancy in between filled states. We can understand this by dropping free electrons of a metal one by one into a potential well. We will explain this in the next slide. Consider the figure. In this figure, the first electron dropped would occupy the lowest available energy E0, and the next electron dropped also occupy the same E0 level. The third electron dropped would occupy the E1 level and so on. That is, Fermi-Dirac distribution obeys Pauli's exclusion principle. In this case, the energy value E1 is found to be greater than E0. The highest filled energy level, which separates the filled and the empty levels at 0 Kelvin, is known as Fermi level, and the energy corresponding to this is called Fermi energy. Fermi energy is the highest energy possessed by an electron in the material. The probability that a particular quantum state at energy E is filled with an electron is given by Fermi-Dirac distribution function, that is represented as Fe. The value of Fe is given by Fe is equal to 1 by 1 plus exponential E minus Ef by kBt, where kB is the Boltzmann constant, T is the temperature. Substitute T equal to 0 in the Fermi-Dirac distribution. We have F equal to 1 by 1 plus exponential E minus Ef by kB into 0. The value is 1 if E less than Ef, and the value is 0 if E greater than Ef. At T greater than 0 Kelvin, F is equal to 1 by 1 plus exponential E minus Ef by kBt less than 1 for E less than Ef, greater than 0 for E greater than Ef, and is equal to half for E equal to Ef. Thermionic emission. The metals emit electrons when they are heated to a high temperature. This phenomenon is called thermionic emission. Since the electron emission does not take place spontaneously, electrons in the metal may be considered to be inside a potential well created by metallic ions. Then suppose the energy of the electrons in the well is W. Then only those electrons whose kinetic energy En associated with the motion normal to a surface of the metal greater than W can escape through the surface barrier. If the surface lies in the YZ plane, the electrons which have energy, that is Ex equal to half mu x square greater than W, will escape through the surface. The number of electrons per unit volume with the momentum between P and P plus dP is given by NV dP is equal to 2 by mh cube into dpx dp by dpz into Fe, where Fe is the distribution function. The number of electrons leaving per unit area per unit gain, that is given by n equal to integral nb dp into Vx. That is n is equal to substituting these values from the above equation, n equal to 2 by mh cube integral minus infinity to plus infinity dpy integral minus infinity to plus infinity dpz integral square root of 2mw to infinity px dpx divided by e raised to beta into px square plus py square plus pz square divided by 2m minus ef plus 1. Since W is of the order of 1 to 5 electron volt and only those electrons whose energies are in excess of W contribute to the emission, we may ignore the term unity in the denominator. So n is equal to 2 by mh cube integral minus infinity to plus infinity dp by integral minus infinity to plus infinity dpz integral square root of 2mw infinity e raised to minus beta into px square plus py square plus pz square divided by 2m minus cf px dpx. That is equal to, that is multiplying these terms, that is e raised to minus beta with px square plus py square plus pz square by 2m minus ef. We get 2 into e raised to beta ef divided by mh cube integral minus infinity to plus infinity e raised to minus beta py square by 2m dpy integral minus infinity to plus infinity e raised to minus beta pz square by 2m dpz integral square root of 2mw infinity e raised to minus beta px square by 2m px into dpx. On substituting the integral values, we get 2 into e raised to beta ef by mh cube into square root of 2 pi m by beta into square root of 2 pi m by beta into m by beta e raised to minus beta w. That is, on multiplying these terms, we get 4 pi m by beta square h cube. That is square beta into square beta beta. Beta into this beta beta square. Into e raised to beta into ef minus w. The current density J carried by these electrons, that is J equal to Ne, that is equal to 4 pi m e k square t square divided by h cube into e raised to beta ef minus w. That is equal to 4 pi m e k square t square by h cube into e raised to minus beta 5, where E is the charge on the electron and phi equal to W minus EF. The factor phi is referred to as work function of the metal. And this equation is the Richardson-Dushman equation for thermionic emission.